Hello everyone, welcome. I'm Professor Diwa, and in this video I'll be going over common logarithms, natural logarithms, and the change of base formula. Our objectives are to identify common logarithms and approximate them with a calculator, evaluate common logarithms of powers of 10, identify natural logarithms and approximate them with a calculator, evaluate natural logarithms of powers of e, use the change of base formula. Okay, so let's get started. First, we have the common logarithm. It states here log of x means log base 10 of x. So whenever you see a logarithm without a base, it's understood that the logarithm is common log with a base of 10. For example number 1, use a graphing utility to do the following. For part A, calculate log of 8 to 4 decimal places. So on the graphing calculator, we hit the log button on the left, we press the number 8, we put a close parenthesis, and then we hit the enter button. So the calculator gave me the value 0.9030899987, and we need to round this value to 4 decimal places, which is going to be 0.9031. So our final answer is 0.9031. For part B, we need to graph the function f of x equals log of x in an appropriate window. Afterwards, we need to use the table function to complete the ordered pair, parentheses 7 comma blank, and parentheses 10 comma blank. First, we graph f of x equals log of x in our graphing calculator. To do this, we need to go to the equation editor by pressing the y equals button in the top left corner. Next, we enter in log of x for y1, we put a close parenthesis, and then we hit enter. To display the graph of this function, we need to press the graph button in the top right corner. Now, if your graphing calculator didn't give you a standard graph that goes from -10 to +10 on the x and y axes, then you could press the zoom button in the top middle, and in the menu, you want to pick Z standard. This will give you a standard 10 by 10 graph. Now on some graphing calculators, like the one I have here, it looks like the graph of log of x stops right next to the y-axis. Now this isn't true. We actually have a vertical asymptote right on top of the y-axis, and the graph of log of x gets closer to the y-axis as x gets closer to 0. The graph should continue downward and approach negative infinity. However, the graphing calculator just isn't capable of drawing the graph so close to the y-axis. Next, we're going to use the table function. To get to the table function, we press second, and then we hit graph. Now you should see an x and y chart with your x values and the corresponding y values. We need to find the corresponding y values to the x values of 7 and 10. For the corresponding y value of 7, in the column, we only see a 4 decimal digit. But if we highlight this y value, your graphing calculator will show you a longer decimal digit at the bottom of the screen. The corresponding y value to 7 is 0.845098040014. We need to round it to 4 decimal places, so this becomes 0.8451. Next, we could see that the corresponding y value to 10 is just 1. So our final answer is parentheses 7 comma 0.8451 and parentheses 10 comma 1. Next, we have a summary of the properties of logarithms from the previous video. So I just put them in this video just as a reminder or a reference just in case you needed them. It states here if x, y, and b are real positive numbers, b not equal to 0, and r is a real number, then for number 1, we have log base b of 1 equals 0. For number 2, we have log base b of b to the x power equals x. For number 3, we have b to the log base b of x power equals x. For number 4, we have the product property, log base b of xy equals log base b of x plus log base b of y. For number 5, we have the quotient property, log base b of x over y equals log base b of x minus log base b of y. For number 6, we have the power property, log base b of x to the r power equals r log base b of x. For number 7, we have the logarithmic definition. We have log base b of x equals y, which is equivalent to b to the y power equals x. For example number 2, find the exact value of each logarithm. For part A, we have log of 10. To find the value of this logarithm, it's important to know the value of the base. Because the base is not written, it's understood that this is common log. So we could rewrite this logarithm with a base of 10. So this would be log base 10 of 10. And this 10 here has an invisible exponent of a 1. We can use property number 2 to simplify this logarithm. This would simplify to the value of 1. Now, if we didn't remember what property number 2 was, we could also solve this by setting this logarithm equal to x. So we have log base 10 of 10 equals x. From here, we could use the logarithmic definition to convert this into an exponential equation. This would be 10 to the x power equals 10. Next, we use the uniqueness property of exponents. We get x equals 1. So log of 10 simplifies to 1. Moving on to part B, we have log of 1000. Again, this is common log, so we're going to have a base of 10, and we can also rewrite 1000 as 10 cubed. So we get log base 10 of 10 cubed. From here, we could simplify this using property number 2, and we just get the value of 3. For part C, we have log of 1 over 10. To simplify this logarithm, we could rewrite it with the base of 10, and we could also rewrite 1 over 10 as 10 to the negative 1 power. We get log base 10 of 10 to the negative 1 power. After applying property number 2, this simplifies to negative 1. For part D, we have log of the square root of 10. To find the exact value, we just rewrite this logarithm with the base of 10, and we rewrite the square root of 10 as 10 to the 1/2 power. We get log base 10 of 10 to the 1/2 power. Next, we apply property number 2. We get that this simplifies to 1/2. Next, we have a practice problem. Find the exact value of each logarithm. For part A, we have log of 0.001. For part B, we have log of 100,000. For part C, we have log of the 7th root of 10. Alright, so go ahead and pause the video, try out these problems, and then check back with the video to see the solutions. Okay, so let's go over part A. First, we could rewrite this with the base of 10, and we could also rewrite the decimal 0.001 as 10 to the negative 3rd power. We get log base 10 of 10 to the negative 3rd power. Next, we simplify this by using property number 2, and this becomes negative 3. If you didn't remember to use property number 2, you could also work this out by taking log base 10 of 10 to the negative 3rd power and set it equal to x. From here, we convert this into an exponential equation. We get 10 to the x power equals 10 to the negative 3rd power. Next, we use the uniqueness property, and we get x equals negative 3. For part B, we could rewrite this as log base 10 of 10 to the 5th power. This will just simplify to 5. For part C, we need to rewrite this with the base of 10, and we need to change the radical into exponential notation. We get log base 10 of 10 to the 1/7 power. Next, we simplify, and we get 1 over 7. Next, we have example number 3. Solve each logarithm for x. Give an exact solution and an approximation to 4 decimal places. For part A, we have log of x equals 1.2. To solve for x, we just rewrite this in exponential notation, and notice here that we have common log. So the base of this logarithm is 10. We get 10 to the 1.2 power equals x. For the exact solution, we write it in set notation. We have a set of curly brackets and 10 to the 1.2 power on the inside. To get the approximation, we just take 10 to the 1.2 power, plug it into a calculator, and then round to 4 decimal places. We write the final answer for the approximation with a set of curly brackets and 15.8489 on the inside. For part B, we have log of 2x equals 1.1. Again, we have common log, so the base of this logarithm is 10. To solve this logarithm for x, we need to rewrite this as an exponential equation. We get 10 to the 1.1 power equals 2x. From here, we need to solve for x by dividing both sides by 2. We get 10 to the 1.1 power over 2 equals 2x over 2. After simplifying, we get 10 to the 1.1 power divided by 2 equals x. The final answer for the exact value we write with a set of curly brackets. We have 10 to the 1.1 power over 2 on the inside. For the approximation, we just use a calculator to get the value of 10 to the 1.1 power divided by 2, and then round it to 4 decimal places. We write the final answer for the approximation with a set of curly brackets and 6.2946 on the inside. Next, we have a practice problem. Solve each logarithm for x, give an exact solution and an approximation to 4 decimal places. For part A, we have log of x equals 3.4, and for part B, we have log of parentheses 2x plus 1 equals negative 0.5. Alright, so go ahead and pause the video, try out these problems, and then check back with the video to see the solutions. Alright, so let's go ahead and go over part A. First, we rewrite this as an exponential equation. We get 10 to the 3.4 power equals x. The exact value we write in set notation. So I have a set of curly brackets and 10 to the 3.4 power on the inside. For the approximation, we just use a calculator and round the value to 4 decimal places. I have a set of curly brackets and 2511.8864 on the inside. Moving on to part B, we first rewrite this as an exponential equation. We get 10 to the negative 0.5 power equals 2x plus 1. Next, we need to solve for x by getting rid of the positive 1, so I subtracted 1 from both sides of the equation. The result is 10 to the negative 0.5 power minus 1 equals 2x. Next, we get rid of the 2 in front of the x by dividing both sides by 2. After simplifying, the result is 10 to the negative 0.5 power minus 1 over 2 equals x. For the exact answer, we write a set of curly brackets and 10 to the negative 0.5 power minus 1 over 2. For the approximation, I have a set of curly brackets and negative 0.3419 on the inside. Next, we have the definition for a natural logarithm. It states here that natural log of x means log base e of x, where e is Euler's number, which is approximately 2.71828. So whenever you see natural log of x, this is just a logarithm with the base of e. For example number 4, use a graphing utility to do the following. For part A, calculate natural log of 8 to 4 decimal places. So on a graphing calculator, we press the natural log button, which is underneath the log button. We press the number 8, we put a close parentheses, and then we press enter. So the calculator gave us the value of 2.079441542. Next, we need to round this value to 4 decimal places. So our final answer is 2.0794. For part B, we need to graph the function f of x equals natural log of x in an appropriate window. And then afterwards, use the table function to complete the ordered pair, parentheses 1 comma blank, and parentheses e comma blank. So let's go ahead and graph the function natural log of x. We go ahead and go to the equation editor by pressing the y equals button on the top left corner. Next, we enter in natural log of x for y1. We put a close parenthesis and hit enter. To display the graph of this function, we need to press the graph button in the top right corner. So now we can see the graph of natural log of x. It looks very similar to the graph of log of x. Again, it looks like the graph stops right next to the y-axis, But remember, there's a vertical asymptote right on top of the y-axis, and the graph continues downward towards negative infinity as x gets closer to 0. Alright, so the next thing we're going to do is use the table function to complete the ordered pairs. So we need to press second and graph to get to the table function. We have the x values on the left and the corresponding y values on the right. For the x value of 1, the corresponding y value is 0. To get the corresponding y value for e, we're going to need to change the table settings. Notice here at the top it says press plus, and then there's a symbol of a triangle and a table. This is the change in table settings. So we're going to press the plus sign here, and it says change table equals 1. What I'm going to do is just change this value to e. On the graphing calculator, to input the value of e, we need to press the blue button or the second button here, and then press divide and then enter. So over here we have the value for e, and the corresponding y value is 1. So our final answer is parentheses 1, 0 and parentheses e, 1. Next, we need to change our table settings back. So move your cursor over to the x value of 0 and then press the plus sign. What we want to do is change the table settings back so that all the x values increase by 1. So change the value to 1 and press enter. And now everything's back to normal. Next, we have example number 5. Find the exact value of each natural logarithm. For part A, we have natural log of e to the third power. What we need to do here is rewrite this as a logarithm with a base of e. We get log base e of e cubed. To simplify this, we use property number 2, which gives us the exact value of 3. For part B, we have natural log of the fifth root of e. Again, we need to rewrite the natural logarithm as log base e and rewrite the radical as an exponent. We get log base e of e to the 1/5 power. After simplifying this using property number 2, we get the final answer of 1/5. For part C, we have natural log of 1 over e to the 24th power. Again, we just rewrite this as log base e, and we also rewrite 1 over e to the 24th power with the negative exponent. So we get log base e of e to the negative 24th power. This simplifies to negative 24. For part D, we have natural log of e to the negative 5th power. Again, we just rewrite this as a logarithm with base e, so we have log base e of e to the negative 5th power. This simplifies to negative 5. Next, we have example number 6. Solve each natural logarithm for x. Give an exact solution and an approximation to 4 decimal places. For part A, we have natural log of 3x equals 5. The first step is rewriting this as an exponential equation with a base of e. We get e to the 5th power equals 3x. From here we solve for x by dividing both sides by 3. We get e to the 5th power divided by 3 equals 3x divided by 3. After simplifying, we get e to the 5th power divided by 3 equals x. Next, we write our exact answer in set notation. So I have a set of curly brackets and e to the 5th power divided by 3 on the inside. For the approximation, we just use a calculator. We take e to the 5th power divided by 3, and then we round the results to 4 decimal places. We write the final answer for the approximation in set notation. So I have a set of curly brackets and 49.4711 on the inside. Moving on to part B, we have natural log of parentheses 3x minus 4 equals 2.3. Again, the first step is rewriting this in exponential notation with a base of e. We get e to the 2.3 power equals 3x minus 4. Next, we need to solve for x by getting rid of the minus 4. We just add 4 to both sides of the equation. The result is e to the 2.3 power plus 4 equals 3x. Next, we get rid of the 3 in front of the x by dividing both sides by 3. We get e to the 2.3 power plus 4 divided by 3 equals 3x divided by 3. After simplifying, the result is e to the 2.3 power plus 4 divided by 3 equals x. Next, we write our final answer for the exact value in set notation. We have a set of curly brackets and e to the 2.3 power plus 4 divided by 3 on the inside. To find the approximation, we just take e to the 2.3 power plus 4 and divide it by 3 using a calculator. Afterwards, we take the result and round it to 4 decimal places. We write the final answer for the approximation in set notation, so I have a set of curly brackets and 4.6581 on the inside. Next, we have a practice problem. Solve each natural logarithm for x. Give an exact solution and an approximation to 4 decimal places. For part A, we have natural log of 5x equals 8. For part B, we have natural log of parentheses 2x plus 1 equals negative 0.5. Okay, so go ahead and pause the video, try out each problem, and then check back with the video to see the solutions. Alright, so let's go ahead and go over part A. First, we rewrite this in exponential notation. We get e to the 8th power equals 5x. Next, we solve for x by dividing both sides by 5. We get e to the 8th power divided by 5 equals 5x divided by 5. After simplifying, we get e to the 8th power divided by 5 equals x. We write the final answer for the exact value in set notation, so I have a set of curly brackets and e to the 8th power divided by 5 on the inside. For the approximation, I have a set of curly brackets and 596.1916 on the inside. For part B, we rewrite this as an exponential equation. We get e to the negative 0.5 power equals 2x plus 1. Next, we solve for x by getting rid of the positive 1. We just subtract 1 from both sides of the equation. The result is e to the negative 0.5 power minus 1 equals 2x. Next, we get rid of the 2 in front of the x by dividing both sides by 2. We get e to the negative 0.5 power minus 1 over 2 equals 2x over 2. After simplifying, the result is e to the negative 0.5 power minus 1 divided by 2 equals x. We write the final answer for the exact value in set notation. I have a set of curly brackets and e to the negative 0.5 power minus 1 over 2 on the inside. For the approximation, I have a set of curly brackets and negative 0.1967 on the inside. Next, we have the change of base formula. If a, b, and c are positive real numbers, and neither b nor c is 1, then log base b of a is equal to log of a divided by log of b. If you have an old graphing calculator or scientific calculator where you can't change the base of a logarithm, then you definitely need to know the change of base formula. In the next example, I'll show you how we apply the change of base formula. In example number 7, approximate the following to 4 decimal places. For part A, we have log base 5 of 3. For this problem, we're going to use the change of base formula, so we get log of 3 divided by log of 5. Next, I just put this into a calculator, and I rounded the value to 4 decimal places. My final answer is 0.6826. For part B, we have log base 1/2 of 5, and again we're going to use the change of base formula. So we get log of 5 divided by log of 1/2. Next, we just plug this into a calculator and round the value to 4 decimal places. The final answer is negative 2.3219. Next, we have example number 8. Find the earthquake's magnitude on a Richter scale if a recording station measures an amplitude of 300 micrometers and 2.5 seconds between waves. Assume that B is 4.2. Approximate the solution to the nearest tenth. We have the equation capital R equals log of A divided by capital T plus capital B. In the box on the right, we have each variable and what they represent. We have that capital R equals the magnitude of an earthquake, A equals the amplitude in micrometers, capital T is the number of seconds between successive seismic waves, capital B equals an adjustment factor. In order to find the earthquake's magnitude, we just need to use the given equation. We plug in the value for A, which is 300 micrometers, the value for capital T is 2.5 seconds, and the value for capital B is 4.2. After substituting all the values, we get capital R equals log of 300 divided by 2.5 plus 4.2. Next, we just use a calculator to take log of 300 divided by 2.5 and then add 4.2. From the calculator, I got R is approximately 6.27918. If we round this value to the nearest tenth, we get 6.3. For the final answer, we state that the earthquake will have a magnitude of 6.3 on the Richter scale. Next, we have example number 9. Find the amount owed at the end of 5 years if $1,600 is loaned at a rate of 9%, compounded continuously. Here we have the equation capital A equals capital P times e to the RT power. In the box on the right, we have each variable and what they represent. Capital A equals the amount owed after t years, capital P equals the size of the loan or the principal, R is the interest rate, and T is the time in years. To find the amount owed at the end of 5 years, we just use the given formula. We plug in the value for P, which is $1,600. We plug in the value for R, which is going to be 0.09, and we plug in the value for T, which is 5 years. We get A equals 1,600 times e to the 0.09 times 5 power. Next, we just plug this into a calculator to find the value. We get that A is approximately 2,509.299497. After rounding this value to 2 decimal places, we get that the amount owed at the end of 5 years is $2,509.30. Alright, well this is the end of our video. Thank you very much for watching. I'm Professor Diwa, and I'll see you in the next one.